There. I'm not ready. All right. So, just like last time, every day is the same. We're going to start working through these chapter 2 slides. I don't love the order there, but that's okay. And I'm going to just hop in and mute everyone just in case. Okay. Because it is super scary when all of a sudden the speakers go on. Okay, but before we start chapter 2, which I think is just called summarizing data, maybe we can write that. Oops. Summarizing data. First, we're going to talk about just kind of summarizing numerical data. And then in 2.2, we're going to talk about how do we summarize categorical data. Right? And we kind of introduced these things last day, especially categorical data, because there's not a lot of things that we can do with categorical data. How many people were in each of these categories? Well, what if we make it a percentage? There, that's it. That's all you can do, basically. Whereas numerical data, there's a lot to do, and so it's going to take us a little while to get through 2.1, and then 2.2 is just itty-bitty. But as a little bit of review, there's a lot of terminology, right? But today, we're going to really be working on those variables, right? And so getting used to hearing and saying variables is a good idea, right? We can have a variable, and what we said was that variable can be either numerical, oops, or categorical. And I also said, depending on what field you're in, you might have other terms, but those are the terms that we're going to stick with. Okay, and so numerical, we're going to summarize numerical data in 2.1, and then, like I said, in section 2.2, we're going to summarize categorical data. Okay. Let's remember, I guess it works since it's binary, right? The question, what was the question that we were supposed to ask ourselves to determine if I could be convinced that it's a numerical variable? If I could be interested in the average of that thing, I would call it a numerical variable, right? Sometimes, depending on what we're studying or what we want to talk about, maybe I would turn it into a categorical variable, age groups, income groups, right? That kind of thing. We see that often. But the question that we're gonna, and there's like a little extra on there, but to determine if a variable is that me? I don't know. Recording in progress. Yeah, I hope so. Although halfway through class, I'll be like, is it recording? Can't remember. Is a numerical variable we ask, would I be interested in the average of this variable? Would I be interested in the average of this variable? Yes, it's numerical. And if no, well, there's only one other thing, one other option. So then it must be categorical. Yeah. So that's just a quick rule of thumb, right? And so I find that that's really, really helpful. the assignment. I was setting it up by your icon. Someone messaged me and was like, hey, when is this assignment that you mentioned going to be up? And I was actually just working on it. And then I was pulled away and I never finished. That's okay. From the day that I post it, you'll always have at least a week to do it. So don't worry. But how about I'll post it today? So it's pretty much done. I just need to link the two systems. It's really easy. It's one of those things. Should have just finished it. But anyways, sorry about that. You'll have an assignment for the weekend to enjoy for next week. Okay. So numerical data. There are way more things, more fun things, cool things that we can do with numerical data. And so let's see here. One of the things that we saw last day was we saw a scatter plot, and there are lots of cool kind of websites and things where they've generated this dynamic data that you can change the year and see how it changes. I feel like bubble charts really took off. I want to say kind of around 2012-ish. They really just like kind of, I think it was a new thing that you could do and people were exploring things. But if you want to watch a really, really fun talk about watch any talk by Hans Rosling, a Swedish statistician. He has passed away, sadly, because his presentations are just top notch, and so they're always statistical. And he just does a really great job of talking about mostly demographic data, kind of population-based data, things like, I don't think this is one of his because his look better, but life expectancy in years and the children per woman, which is supposed to measure total fertility. And so what does this tell us? Our skills from last day tell us that, okay, all we really know is, well, there's a lot of things we know from last day, actually, as a little bit of review. The life expectancy, we would call it the response variable because it's on the y-axis, right? And so here, this would be the response variable because it's on the y-axis. We would call the children per woman per woman total fertility the explanatory variable. This is in the year 2011. You can flip through the years. I think I encourage you to check out the website, but I think when I did, it changed. And so I don't know where it is anymore, but that's okay. Gapminder.org probably still hosts it somewhere, but we can talk about, does there seem to be an association here, a relationship here? Just kind of broad strokes, I would say that there is. In fact, the best shape that I can think of to describe this thing would be linear, right? It looks like a line to me. A straight line would model this behavior, right? And so here, right, looks linear reasonably. And it looks like it's a negative relationship. Meaning as your x's increase, your y's are decreasing. And so they do appear to be associated, right? And we can model this behavior with this straight line, but we're gonna hold off on getting to do that until much later in the course. So we already know a lot of things about kind of visualizing data, and we've looked at a scatter plot last day, and so we've established all these terms, and we can do quite a bit with that already, it turns out. Can you believe that? I guess you can. So as a side note, here we're introducing all these different plots that we could use for numerical data. Now, I want to make a note right away that for us in this course, for a single numerical variable, we're going to be using histograms to visualize them. Okay, and so note, this course, we will use histograms, which are introduced later. And so they are coming, but we introduce all these kind of weird things that we can do, and then we settle down into histograms. We will use histograms to visualize numerical data, or I'll say a single numerical variable. See how important it is to have a handle on those terms, right? We have to, well, we haven't talked about a histogram yet, but one single numerical variable, we have to know what that means, right? It's just a column of data with numbers. I wouldn't call a dot plot useful because I don't find that they're very nice to look at. But if you have to describe what a dot plot does, here's an example of a dot plot. What does it do? It layers, these are all the same colored dots, presumably something like this. And the darker it gets, the more dots there are on top of each other, right? And so here, oh, I guess I don't need to write it because darker colors represent areas where there are more observations. I find that that's really difficult to look at and to figure out kind of what's happening here. But if we had to take a stab at it, right, it looks like, okay, I've got a few here, and then it kind of gets dense up around coming towards 3.5 up to 4, right? It gets kind of dense. What am I doing? Just kind of potentially intuitively, I'm kind of looking at this and going, okay, it must be increasing here, increasing. Maybe something like that. That's the distribution of this data. So we would call this the distribution. We're going to talk a lot about distributions, especially today. And so how would you describe the distribution of GPAs in this data set? So like we said, we can talk about where does it look like things are centered. I would kind of center them just above 3.5. That's completely somewhat arbitrary, right? I'm just kind of looking at this and looking at where the center of the most of the dots are. It looks like around 3.5. And then the shape, well, looks like it's increasing as we head towards 3.5, like we were saying. And then we can also pull in the spread, right? Looks like somewhere between 2.5 and 4 is where all these GPAs are, right? That kind of captures all the GPAs. So like I said, I'm going to be rude and add not very useful for visualizing one numerical variable. I don't know. They love starting with it, but I don't. Somewhat better, just like a little bit better, is the stacked dot plot, which does the exact same thing, except what? It takes all those kind of dots that are on top of each other and just stacks them a little bit. Like this. Right? Now it's a little bit easier to see this distribution, right? And so here, right, again, now each dot represents one GPA, right? They're all the same color. And so now we just stack them on top of each other. Okay. Ready for a histogram? So histograms do the same thing, okay? We still use them to visualize the distribution, but instead of looking at individual data points, right, what we do is we just put them in bins, okay? And so this is generically what a histogram looks like. And so we've got these bins here. This is a bin. In this case, we changed from GPA, so I guess we were over it, but the hours per week spent on extracurricular activities, right? Anyone who gave an answer between 0 and 10 gets put in this bin, right? And so then, just like the stacked dot plot, every individual in there takes up some space. And so on this axis here, we have the count, or if you prefer, the frequency is usually what it says when we're using software. So from this histogram, you can tell me things like how many students in the data set spent between 0 and 10 hours per week spent on extracurricular activities. Must be 0, 1, 2, 3, 50, 100, 150-ish, right? How about between 10 and 20 hours? Well, looks like about, I don't know, 30 or so. Hard to say, right, without an axis, but roughly. Okay. And so what have we done? When we make these histograms, we're temporarily creating categories, right? The bins are the categories, right? And so we're not overwriting our data with these categories, but we are kind of temporarily treating them as categories. Now we can adjust the bin width in this case being 0 to 10, 10 to 20, 20 to 30, blah, 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 right? And so then we might see more details or sometimes too much detail if we have a really small bin width. Okay. And so here, trying not to get ahead of myself here. Okay, I will highlight histograms. They're the most important. We can think of the bins as temporary categories. And we can change the bin width if we would like. This is more of an Excel or any sort of software problem. We're not going to make histograms by hand. That's crazy. Okay? But we do need to be able to look at these things and say, okay, what I'm understanding here is that each observation between 0 and 10 is getting stacked on top of each other. And that means that here I have very few observations in the 30 to 40 range. And then this poor one here, there is a little observation here in the 60 to 70 range. Or maybe I shouldn't feel bad. Maybe they're just doing hobbies all the time, counting it. I don't know. Okay. And so we use these to visualize the distribution. Right? So we can adjust the bin width, like we said, right? And so this is all the same data. There is kind of a problem, which we wouldn't think was possible, right? But just kind of revealing too much about the data. Because when we're trying to visualize data, what we're really going for is just kind of broad strokes in general. What does this group look like? Because the problem would be, okay, this is a sample. And just like we were saying last day, what we're truly interested in is the population, right? And so if we focus too much on what this exact sample looks like, then we lose that kind of transferability to the population, right? And so that's why you don't want to reveal too much, because it's just the sample that you're looking at. And the sample, if you've collected properly, should be kind of reasonably representative of the population, right? And so you kind of want to squint a little bit when you're looking at sample information, right? Because they're just a mini version of the population. And we understand that if I took a completely different sample, right, of extracurricular hours, it would look a little bit different, but generally the same, right, is what we're hoping. And so that's the problem with revealing too much, is that it becomes too sample specific. How about let's talk about what the bin width is here first. The bin width in this case would be 0 to 50. That's probably bad, because we just lumped everyone in 0 to 50, which was pretty much everyone, right, into one bin. You could, but it doesn't tell you very much about the data, right? So here, bin width here seems to be 50. Right, because this, I'm assuming, is 50. Of course, 49.9 and 50 or something like that. But we're not too picky. What's the bin width? We move across this way. I'll zoom in a little bit so we can see. 0 to 10, 10 to 20. I'm gonna call the bin width 10. That looks good to me. I'm happy with that, right? So here, I'm sad because I don't learn anything about the data. Here, I'm happy with this. Whee! That's okay. What about the next one? Now we've got a bin width of 5, looks like to me. I'm happy with that. Gives me a little bit more detail than the 10, right? Because there are so many in this first stack, it is nice to see that, okay, there's actually a lot of people just in the 0 to 5 range. And so I'll give it a double smiley. If I could draw thumbs up, I would, but you guys are probably too young. Do you know what a capital Y in brackets is? It's a thumbs up. It's when we had to type out our emojis. Yes. This is a thumbs up emoji. When I first started teaching, I would do Y's in brackets on tests and stuff as I was marking. Like, cool. Maybe I should start doing that again. Have fun. Now, well, you have to know what it means. Now you know. Who did know that though? Nice. What happens here at a bin width of, what is that, 2? 1, 2, 3, 4, 5 bars in a length of 10. I'm gonna go with 2. This becomes too sample specific, right? This dip here, for example, is likely just from the sample, right? Not necessarily what's going on in the entire population. If you were to use something like this, how I would encourage you to read this, or to kind of read the distribution. Oops, maybe not down like that. It would be something like that. You just kind of close one eye and squint a little bit and just kind of drape something over it, all right, to get the general idea. But this is a little bit too specific. Too sample specific. Okay. A little bit. Right, I'm forced to ignore this tall one, ignore these dips. Right, it's a general shape that I'm going for. Okay. I usually just go with the default bin width that Excel does. It used to be, until I want to say in the past 3-4 years, that Excel put out a histogram function where it can generate a histogram. You used to have to kind of cobble them together, reduce the spaces and tell it the bin width. And it was crazy how long it took them to produce something. But now we can just ask it to make a histogram and it just picks an appropriate bin width. And that's usually what I would encourage you to go with, right? You can play around with the bin width, but I just always use the defaults. Any questions so far? I mean, technically you could do 0 extracurricular hours. Usually we just start at 0 for niceness. It just looks better. But yeah, I'd say 0 is a possibility. You do nothing else, nothing extracurricular.
Between that 2, half an hour.
Yeah, anything less than 1 would get kind of lumped into 0. But good. One of the things when we talk about a shape of a distribution, which is going to be super important, because just like knowing what type of variable I have, if it's numerical or categorical, if I've decided, okay, I have a numerical variable, then the shape of this thing will determine what's appropriate to do, okay? And what the appropriate center and spread are. And so that's what we're building up towards, is just kind of being able to describe the shape and then the center and the spread as appropriate of a distribution. So one of the things that we're going to talk about is modality. A mode is a peak. Yeah. So does the histogram have a single prominent peak? Again, not getting hung up on sample specific things, but just kind of blurring the lines a little bit. Okay. If it only has one single peak, we call it unimodal, right? One mode, uni meaning one, modal is the mode. If you have several prominent peaks, if you have 2 peaks, then bimodal would mean, or I should use a different color, is the specific case of 2 modes. Anything after 2, we just call it multimodal. What you'll find is there are always clues in the words, right? So I love etymology. Etymology is kind of the origin of words and where words come from, probably because it is so helpful, right? And no apparent peaks means that it would have some uniform distribution, just kind of even, right? And so what we're going to do is, right, just got a note here, but what you're going to do is just imagine a smooth curve over this histogram, right? You don't want to get hung up on little things like this, right? And so you don't want to be looking at this and going like this and calling it bimodal. That's not true, right? They have to be prominent peaks. And so what this is going to look like is just kind of like this. I like her, imagine that the bars are wooden blocks. I don't know why they have to be wooden blocks, but you drop a limp spaghetti over them and they just kind of look at what the spaghetti looks like. I think we can do that, but just kind of a fun thing to think about. So here, this, I would call this unimodal, right? One mode, one prominent peak at roughly 4, 3.5-ish. Okay. I guess I should write that. Unimodal, where the mode is roughly at 4, let's say. Right, somewhere around here. Ish. It's a lot of ish. Okay. The next one, there's no denying, right? We are going to have 2 prominent peaks. Generally, the shape. So this I would call bimodal. And the modes seem to be, I don't know, roughly around, let's say 4 again, and I don't know, 18-ish. It's all ish. roughly 4 and 18, roughly. This is supposed to be an example of a multimodal distribution. Seems logical, right? I would probably not be too concerned about this dip, but since we are kind of meant to be, concerned about it, I'll just kind of do something like that. Putting modes around, I don't know, 3.5, 3, 12, and let's say 18 again. Multimodal with modes around, I don't know, let's say 3, 12, and 18-ish. Without the scale and without, because we all imagine our little lines a little bit differently. It's fine. There are mathematical ways of finding the modes that we'll introduce. Usually the Excel function mode of this data set, and then it'll return the data or the information. This, you could try to see some sort of shape there, but I would call it uniform. So when it's just kind of a box, then we say that it's a uniform distribution, which is really boring. There's nothing going on, right? And so each category has essentially the same amount of activity. But it's one of the distributions that we need to be aware of, that it exists, but we'll never really analyze a uniform distribution because there's nothing to learn there, right? If, and I'll start that here, if a distribution is unimodal, right, meaning it only has one mode, then we can talk about skewness. So if a distribution is unimodal, we can discuss skewness. We know words like askew, right, meaning kind of off to the side, right? And so skewness is exactly that, where we've got this kind of skew in our distribution. And so our options are going to be right skewed, left skewed, or symmetric. Okay? Symmetric about the mode. I'll add that here. Symmetric. I usually say about, but maybe I'll say around the mode, just to emphasize that it would be symmetry around the mode. One of the things that's going to be really important to remember is that the skew is always in the direction of the tail, right? And we haven't talked about the tail, but let's see here. You're going to draw something like this. Where would you say the tail is? Probably here, right? Kind of capturing these smaller values out here, okay, more extreme values. And so first we'll start with the tail. I think it's human nature to want to talk about oh, it's skewed towards these guys because this is where most of the data points are. But that's wrong in stats, okay? And the reason for that is we always have the skew in the direction of the tail, because in statistics, what we're interested in are these kind of extreme observations. We're always interested in those little guys. What happened here? How extreme are they, right? And so the skew is always in the direction of the tail. So here, note, the skew is in the direction of the tail, which is potentially counterintuitive to how you would say it, right? So that's something that you need to kind of put a stop to. Maybe take stock, right? Which one would you say kind of intuitively? For me, when I first started, I always wanted to talk about the lump, but we don't care about the lump because that's where everyone else is, right? We're interested in these extreme observations. So if it's skewed in the direction of the tail and the tail is to the right, then this would be a right skewed distribution, or skewed to the right skewed right, or if you want to say positively skewed, right? It's skewed in the positive direction. You're welcome to use either one of those. I'll use right and left for the most part. Okay. But if you prefer positive, negative skews, that's totally fine too. And again, it's one of those things that you have to keep track of, right? Use them interchangeably. Pick one that you like, but just when you're reading, right, know that they're interchangeable. So here, on the next one, just a little tail, but now the tail is to the left. And so this would be left skewed or skewed left. Or negative skew. Left skewed, skewed left, all the same. I'll highlight. It's the same note that I made earlier, but now it's on here twice. Now, for this last one, it would be pretty picky of me to pick a skew in this case because it looks to be relatively symmetric about the mode. Okay. And so here, I would say this is symmetric about the mode. Roughly. Right, there's some leeway there. Okay. This shape, I'll introduce it now, is going to be really, really important for a lot of our analyses. It's going to be called the normal distribution, which is a name, but we can call it the normal distribution. And a lot of things are naturally normal. Yeah? So they just kind of follow a normal distribution. And so this shape is called normal just want to introduce it now. Or bell curve. Right? Pretty old school, but oh, I grade on a bell curve. What does that mean? Knowing what that distribution looks like now, right? Everyone's hanging out at some point, and then you decrease in either direction. Right? Your grades until you reach a minimum and a maximum. Right? You can determine the center there, right? But grades do generally fall on a bell curve or a normal distribution. And so that's kind of interesting. But like I said, a lot of things follow a normal distribution. But we'll come back to the normal distribution. We'll spend a lot of time with it a bit. Any questions so far? Okay. So like I said, a lot of our concern is going to be with those extreme observations, right? And potential outliers. So outliers, wait. Right. We want to talk about unusual observations, extreme observations, outliers. When we talk about the shape of a distribution, we can talk about the shape in general and then add, with the exception of a few outliers. Okay, so here, for example, if I had to talk about the shape here, I would say the first one is skewed to the right, in the direction of the tail. So here, skewed right. Saying that it's skewed to the right tells me that there are outliers in the upper end, right? And so here, outliers on the upper end. That's implied with the skew. But you might want to mention, oh, okay, and then there's definitely an outlier or something like that. Here's an example of where I would stick to the general shape. What does this look like? This looks like a normal distribution, right? And so this looks like a normal distribution with the exception of a few outliers on the upper end is how I would describe this. So this looks like a normal distribution with the exception of a few outliers on the upper end. So that's how I would describe that distribution. As soon as you say there are outliers, you have to do a little bit of work to determine if they are actual outliers, and we're going to have math to help us do that. But we can also just look at it visually and say, oh, I suspect that these guys are outliers. Have you read the book Outliers by Malcolm Gladwell? He's probably one of my favorite authors. He does all these kind of they're like statistics, but for fun reading, kind of like Freakonomics in a way. But he does a really great job. Outliers. I can recommend it when you can read for fun. I know you're not in that phase right now of your life. And maybe when you're reading for fun, you don't want to read a stats book, but it's really good. how would you describe the shape of the distribution of hours per week students spend on extracurricular activities? Now, a note before we do this. I want you to imagine, I always think of this study, it's a fake study, but where they did this kind of mock study of which fruit people would grab to pretend they're talking on the telephone. And it's always the banana. You got a fruit bowl. Now grab a fruit and pretend you're talking on the phone. Everyone goes for the banana, obviously. Anyways, just kind of a funny thing. But so what I want you to do, I'm holding over the microphone. What I want you to think about doing, if you're going to describe this to someone on the other end, so someone who can't see it, right? You need the terms to explain it, right? But also you need to cover 3 things in order to fully describe what this looks like. Oh, so I've got this data. Oh, I guess I shouldn't cover my microphone. So I've got this data. Oh yeah, you won't believe what it looks like. Oh, tell me. Okay. Well, first, the shape. Skewed to the right. Oh wow, crazy. Yeah, I know, right? Like what's the range of your data, right? Somewhere between 0 and 70. That range, or that kind of spread, gives me a pretty good idea of, okay, these are some reasonable values, right? And then, oh, you got to tell me, where is this thing centered on? Oh, it looks like it's, I don't know, somewhere between 0 and 10 hours per week, right? And so talking about the shape, the center, and the spread will fully describe this distribution, right? Is there anything else missing? No, right? I don't know what else I could talk about. I could go into detail about kind of the height of each bar, right? But that would be a little bit overkill, because talking about the shape, the general shape, and the center and the spread is going to be enough. Where am I going to write this? To fully describe a distribution, we need to talk about 3 things, or we need to know 3 things. One is the shape, which in this case, I said is skewed to the right. You could even say heavily skewed to the right or something like that, right? But skewed right. The center. Where is this thing centered? Now the center is going to be kind of tricky, but we'll do the center is where the bulk of the data is. So typically we talk about the mode. So the center is approximately 5. We're just eyeballing these things, right? We're just talking about, oh, is it in the 5s, or is it on along the scales of 50 or 50,000, right? We're just talking about magnitudes. And so somewhere between 0 and 10 is good enough, right? But it's always nice to kind of have a number. And so you could have said between 0 and 10. That's good enough, right? Just approximate ideas. And then the spread. By the spread, in this case, I just mean kind of minimum to maximum, roughly, right? Usually, even if the data goes a little bit beyond the last number here, I would just pick the number that's shown on the axis, right? Just rough approximations, right? Does it go from 0 to 10,000? No, it goes from 0 to 70 reasonably, right? Just to give an idea. And so here, 0 to 70. The minimum to the maximum. That's what you want to do. So that's pretty cool. You can describe an entire distribution by those three things. Right? Easy marks on the test for sure. I will give you a distribution and ask you to describe it. Well, shape, center, spread, you're just eyeballing things, right? And so that's kind of fun. That's like 1 mark in the bag already. Out of how many? Oh, now you see the importance of the range. Out of 24,000. No. 24 probably. It's pretty good. Nah, I think I like to keep them around 30, 40, something like that. So we've already talked about these little guys, but here that is a summary, right? And so, of course, only a unimodal distribution can have skew, at least in this course, right? And so then we have right skew, left skew, and symmetric. One kind of important skill to have is when you're collecting data is having an idea of roughly what shape are you expecting to see, right? And so if you're collecting data on heights, for example, right? Everyone's kind of hovering around the same height, but then there's some shorter people and some taller people. And it's one of those things where we just have a naturally occurring normal distribution, right? And it's normal because it happens all the time in all these things that we measure. Okay? And so a uniform distribution, remember, is something like this, right? That's kind of boring. Not really going to come up, but that's okay. We can think about it. Like I said, a lot of, there are some things, so some kind of quick references. Any measurement that we do, so weights, distances, all those things are typically normal. Okay? And so weights and heights and maybe I should say tend to be normal. Hard to answer this question without this background information, but one of our main things that we're going to keep in mind is that anytime we have money, right, salaries and house prices and prices in general, they tend to be skewed in which direction? Skewed to the right, right? A lot of people, or a lot of kind of prices, I guess for income especially. Let's think about income because house prices a little bit different. Sort of. What would you expect the salaries to look like? Something like that, right? Skewed to the right. Same thing, house prices. There's not very many at 0, but there's a lot kind of in one range, and then there's just a few in the very, very upper range. Okay. And so here, what I want to say is money, generically money, is skewed to the right, just in general, right? There are instances where it's not, but is often skewed right. Birthdays of classmates in the day of the month. I don't have any reason to think that more people are going to be born on the 1st than on the 2nd or the 3rd or the 4th or anything like that, right? So now on my graph, right, I'd have the 1st of the month, the 2nd of the month, 3rd of the month, all the way up to, I guess it gets a little bit kind of weird after 29, 28 February, right? If you're born in February, difficult to hit 29, possible, right? Whereas if you're born in April, 29 is really easy, right? But in general, 29, 30, 31, I would expect kind of a uniform distribution, right? I'm sure there are studies that have been done where some days are kind of more common than others, but not significantly more common, right? And so that's what gives us this uniform distribution. So the day of the month would be here. I'm not. I don't love this one. I know it's the first activity. Well, we basically already did it with the previous one, right? But you can sketch the expected distributions, right? Number of piercings. I say we're not going to do it, and then I'm going to talk about it. So we can start at 0. People very reasonably have 0 piercings. 1, okay. Usually kind of ear pierce is the gateway. So usually we kind of start at 2, right? And then if you're trying to get back at your mom, you get a 3rd one, and she pretends like she didn't even notice. I was so mad. Good for her. Etc. And then there's very few people who have a lot of piercings, right? But very few. So what does that look like? I know I said we wouldn't do it. Something like that. Right? It's a good skill to have, but let's move on. On to some math. Okay. First thing we want to establish is that the mean is just the average, right? We tend to call it the average, but in stats, we call it the mean. And so the mean is the average. I'll use them interchangeably. Okay? So it's your job to keep track of, okay, they mean the same thing. You're welcome to use whichever term you'd like, but a lot of the time we'll just end up calling it the mean. Okay? And so the mean, okay, let me see. There's a lot of things that I want to introduce on this one slide. So how about this? I'm going to add a page here and kind of break it up. Add a page and Okay. First of all, some notation. We're going to be talking about, it's already italicized and blue, but I'll highlight it as well for good measure. Okay. The sample mean is, so I've collected a sample, of course, and then I'm able to calculate the average, right, and the mean. So if I give you a bunch of numbers, let's say, for example, the data I've collected, the variable is called X, just generically called X, and the variable that I've got here is 425. If you had to find the average of this, what would you do? Add them up, divide by 3. You already know how to do this, right? You know how to find the average. Okay, but what I want to do is just kind of link it to the notation to show you that you already know what this all is. Okay, and so here, what we can do is we can say just generically the first entry is X subscript 1, X1, right, in X. Because we need these placeholders, right, just for any data set, not just this one data set. X1, X2, X3. In this case, we've already talked about N. N is 3. N is the sample size, right? Has to be a lowercase n because it's a sample size. Whereas capital N is the population size, but we don't worry about that. Okay. So the average, right? What are you gonna do? You would add these up, 4 plus 2 plus 5. Well, generically, that would be X1 plus X2 plus X3, right? X1 plus X2 all the way up to Xn, right? Allowing for any number of sample sizes. And then what? You would divide by 3 in this case, but that's because your N is 3, right? And so here, divided by N. And so that's how we get this, this notation. X bar denotes the mean of X, right? Or the average of X. Or average of X. Yeah. X is just a placeholder for the variable name. Yeah. And so we can do things like age bar is the average age. Does that make this? Your average smiley face. Anything with a bar over it is the average, right? Or the mean. Anything with a bar over it is not just the mean, but the sample mean. Okay, it's going to be really important that we distinguish between the two. Sample mean. We can condense this even further with summation notation. Fun to say, fun to do. Summation notation takes this. So a capital sigma we're going to be using a lot of Greek letters. And so capital sigma looks like this. Usually it has little kind of what's it called? Serifs? Yeah. Serif font, sans serif. This is a summation. This is a capital sigma. And so what it does is it goes from I equals 1 to n. You can kind of ignore that as long as you know that what it's going to do is it's going to add up all your x subscript i's together, right? Add up all the x's. So this is summation notation. Which you're going to read as the sum of xi from x, or I guess technically from I equals 1 to n, right? If I tell you that n is 3, what would, so as an example, let n be 3, then the sum from I equals 1 to n of xi, I can replace it with 3. The sum of I equals, this is an I, clean that up. I equals 1 to 3 of xi. I can expand it out as x1 plus x2 plus x3. Notice that I'm only talking about the numerator here, right? The denominator, I'm still dividing by n to get the average of x, but I've just condensed that numerator with summation notation, making it a little bit cleaner. You already knew to do that though, right? In calculating the average, right? Just, you already know how to do it, but I want to use that knowledge to link it to the summation notation, which is going to come up again, okay, in a less obvious way. Okay? And so now, okay, we've got the sum of the x's divided by n is the average. Sometimes I'm lazy or just the sum of x. I drop all the indices, which is super lazy. And anyone in math would be really upset about that. But in stats, we're kind of like, well, obviously, all of them, right? So we can kind of ignore it. And this will be on your formula sheet. I'm not ready to show you the formula sheet yet, because you'll probably not like me very much after. Or you'll really like me because it's all on the formula sheet. But this is on your formula sheet, okay? And so, but you also know how to find the average, right? In Excel, you can use the average function, right? Type in equals the average and then give it some numbers and it tells you what the average is. Okay. That was the first bit on this slide that I wanted to talk about. How about the second bit? So we've got this kind of tricky situation. Or maybe I'll do this. I can put them all in one. Our goal in statistics is to learn about the population, right? But in order to get there, we collect a sample and then we make sure that it's, or we hope that it's representative of the population. But what does that mean? So now I'm going to calculate the average of my sample mean. But what am I really trying to learn? Trying to figure out what the population mean looks like, right? And so now I've got two different means and I need to be able to keep those separated, right? And so what we're going to find is there's going to be kind of the sample information, or maybe I shouldn't put it there. I'll do the mean can come from the sample, but really what we're trying to learn about is the population, right? The population mean. Okay. So the sample mean is denoted by X bar. And then the population mean is going to be denoted by a Greek letter mu, which you're going to read as mu. If you ever have to type it out, you can just write mu if you want. Obviously, if you're writing by hand, it's easier to just do the mu. It's got this kind of nice flair to it. Just an M, really. But with a little extra. And you're going to read it as mu. And the mu represents the population mean. Right? Another thing that we haven't talked about yet is, but we will, is the standard deviation, which you might have, kind of heard about, or it's often mentioned in studies and things like that. And so same idea, we're going to have this sample version. So a sample standard deviation is denoted by a lowercase s. And then the population standard deviation is going to be denoted by a lowercase sigma. And I know what you're thinking. Emily, wasn't this a sigma? Yes, it is. But this is a capital sigma. Letter sigma. And they're different. So this is a lowercase sigma. So any measurement from the sample is called a statistic. Haha. Wow. So any measurement from a sample is called a statistic. I know, right? And just want to highlight S, so sample and statistic, they go together, S and S go together. And in a very nice, kind of similar way, any measurement from the population is called a parameter. So any measurement from a population is called a parameter. So again, we've got this P and P situation. So one of the main things that we'll be doing is using a statistic to learn about a parameter, right? Or its corresponding parameter, right? We use the sample mean to learn about the population mean, which is really what we're interested in, right? And so we use a statistic to learn about its corresponding parameter. Right? Makes it a point estimate. We'll call it a point estimate. So the sample mean is our best guess at what the population mean looks like. We all understand that if I were to collect a random sample of this group and we talked about, I don't know, average height, for example, right? We could do that, take a random sample of 5 people in this class, calculate the average height. Then I release those people and I take a brand new sample of 5 people and I find the average height. How would you expect that behavior to turn out? Well, it's normal. They're all centered. We all expect the averages to be hovering around the population average, right? If we took everyone and calculated the average in this room, perfectly reasonable, right? Generally not so reasonable, right? But we would expect the average of those groups to be hovering around the population average, but we also don't expect it to be exactly the population average, right? We'd be pretty weirded out if it was way off, right? That can happen, but generally we expect them to be close to the population average. How am I doing? Hey, not bad. Okay. And so here, so the sample statistic serves as a point estimate, which is our best guess. Yeah. I mentioned that here because we're going to be working with point estimates quite a bit later on. And so it's good to get used to that terminology, but we'll also reintroduce it later. Okay. In general, we use Greek letters for populations. Okay, so for parameters, we use Greek letters. And so note, we use Greek letters, probably capitalized Greek. No harm, I guess. To denote a parameter or parameters, right? Which now you know, when I say parameter, you say, yeah, no. When I say parameter, you have that link, or you will have that link that says, oh, that's a measurement from the population, right? And so Greek letters, when you see Greek letters, they're measurements from the population. Yeah. Whereas kind of these Muggle letters down here, X bar, yeah, we did some stuff to it, but these aren't Greek letters. They're just regular letters. I know there's a name, but it escapes me. What is our alphabet? Sold. Regular letters are from the sample. Okay. Which means what? If you've calculated something, right? If you've actually sat down and done the calculation, you've calculated a statistic, right? A sample statistic. Because if you knew everything about the population, then cool, but that's very unlikely and you wouldn't be working on anything like that. So if you have calculated something, it is a measurement from the sample. Therefore, are you guys okay with it? Did I ask already? I feel like I throw it out there often. Therefore, 3 dots in a triangle is therefore. Now you know. In case I hadn't before. Therefore, it is a statistic. Question so far? We're going to start with the variance. Now, okay, so I guess I forgot to say a thing or two, probably a billion things. The mean is a numerical measure of center, is a numerical measure center. The problem is we can always calculate the average, but it's only appropriate if you have a unimodal symmetric distribution. And so the mean is a numerical measure of center. So just like we looked at the shape and then we kind of roughly approximated the center and the spread. Well, now we're going to have numerical measures that do that for us, right? And so the mean is a numerical measure of center. Which is only appropriate for unimodal symmetric distributions. So depending on the shape, that's going to determine the appropriate measure of center and spread. Okay. We're going to start with our go-to kind of normal distribution. What does that mean? It means that here, this center is not just the mode, but it's also the mean. Right. We're going to start with the variance and then quickly move into the standard deviation, which I mentioned up here in our table. Right, the standard deviation is a measure of spread. The variance is also a measure of spread. A measure of, keep saying oops. Maybe I should just be more careful. Never. A measure of spread, right? Appropriate for, again, unimodal symmetric distributions. appropriate for unimodal and symmetric distributions. We will use the standard deviation instead of the variance. They are related. We saw in that table that the standard deviation is denoted by a lowercase s. And now we have the variance is s squared, and that's their relationship. So the variance is the standard deviation squared. Okay. But we'll start there because the formula just looks a little bit better for the variance. So they've got this example here, but what I want to do is just break apart this formula so that we know how to tackle it. And of course, it'll be on your formula sheet, although I think I skipped straight to the standard deviation on the formula sheet. There. S squared is the sample variance okay. This looks bad, doesn't it? Especially if it's been a while slash maybe never since you've seen summation notation and stuff like that, right? But what is this saying? It's saying, okay, so I have the sum from I equals 1 to n. We're okay to ignore that just because, okay, do it to all the things in your data set, right? First observation, second observation, third observation, okay? And so then x subscript I is just a placeholder for each observation, right? And so starting inside these brackets, what do we want to do? From each observation, I want to take away the mean, the sample mean, which means I have to find the sample mean first, right? And so from each observation, subtract the mean. How far from the mean is this thing, right? That seems like a deviation, doesn't it? Right? Yes, it does. Deviation from the mean. Okay. And then what are we, and I'll write down these steps, but I just want to talk you through it first. Then what you're going to do is you're going to square each of those deviations. What does squaring a number do? Presumably, the mean is in the center, and so a lot of values will be below the mean, roughly half, and a lot of values will be above the mean, roughly half, right? Just because of how we've decided, okay, it only works for unimodal symmetric distributions, okay? And so then we're going to have some negative deviations and some positive, but when I square those, they all become positive, right? Otherwise, if I added them all up, what would happen? They should go to 0, right? Should add up to 0. That doesn't help us very much, right? Then we would just have 0 and a variance of 0. That's not what's happening here. So we square them. Squaring them has kind of multiple benefits. Squaring a value, a negative value, turns it positive, but it also amplifies large deviations, right? If you have a deviation of 1 and I square it, then the squared deviation is still 1 squared, which is just 1, right? But what if I increase that by 1? So now I have a deviation of 2. Then what happens? 2 squared, all of a sudden, that's being counted as 4, right? Because it's extra bad, right? So we're kind of penalizing these bigger deviations. Okay, and so that's the benefit of squaring and why we would have to square these values. And then what would that look like in your data set? Right? You've got your data set presumably listed something like this, right? X1, X2, X3, all the way up to, or down to Xn, let's say. And then next column over, you could say Xi minus X bar, X1 minus X bar, X2 minus X bar, X3 minus X bar, boop, 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 Xn minus X bar. If you had to do it by hand. I'm gonna make you do it by hand, not on a test for sure, because rude. But when you have a little bit of time to think about it, an assignment maybe. So I'm gonna cheat here. What's the next column gonna be? If I'm building this out, well, now I'm squaring each of these, bless you. All right. So now I have still n things, but they're the deviations squared. Right. Now I'm ready to tackle the summation, which says, okay, to get this whole chunk, you're gonna add up everything here to get this whole bit. That's going to become one value, right? The sum of all those things. Hard to do and hard to see it without actual numbers, right? But it is important that we learn how to read these formulas and kind of dissect them. And then it's nice to have a look at some numbers and make sure you got it. Okay. But this, I'll do a little. That's how you would get that numerator. And then the denominator, you're on easy street. You just divide by n minus 1. And that's just something that it's on your formula sheet, so you'll just remember to do it. But it is a little bit weird to divide by n minus 1 instead of n, but it's because you want to have, well, there's math reasons, obviously, but the best estimate turns out happens with n minus 1 instead of just n. So, and so let's talk about the steps here. Step 1, subtract the mean from each observation. From each observation. And I'll say to find the deviation. Right. Implied deviation from the mean. Find from the mean. Your second step is going to be square the deviations. Square the deviations. And I'm pretty sure the next slide talks about the benefits of squaring, so I'll save that for then, but we've already mentioned it, right? Makes negative values positive, but also kind of amplifies large deviations. And then you sum all the squared deviations. Sum the squared deviations. And then divide that sum by n minus 1. Good. And of course, Excel can do this easily for us. A lot of calculators do it for us as well. So you can play around with that, right? But being able to read, so I don't care if you can do the math, right? There's all these little typos and things like that. What I do care about is that you can read a formula like this and break it down and know what you would need to do and what's involved. Okay. Standard deviation, let's introduce that here. It's probably later, but the standard deviation, or SD, when I write about the standard deviation, the abbreviation that I use is SD, capital S, capital D. But then in notation, so in my math, it's going to be a lowercase s. Oh, it's getting boggy, isn't it? You can stay on top of it. So the standard deviation is the square root of the variance right. Lowercase s is the square root of s squared plus minus the square root, but we can't have a negative spread, and so I just ignore it. Okay. The square root of s squared, well, s squared was the sum from I equals 1 to n of xi minus x bar squared divided by n minus 1, all square rooted, is the formula for the standard deviation. So this is now the standard deviation. That's why we use the variance as a gateway to get to the standard deviation. In upper level stats, you do use the variance, but it gets a little bit complicated in terms of kind of understanding how squares work. And so that's why we just use the standard deviation in this course. And so, I'm gonna lose my voice. Uh-oh. It's okay. Just gotta hang in there. So the first couple of weeks of classes, all these growing pains. Okay. Like I said, why do we use the squared deviation, right? Get rid of negatives. And then I just want you to think about, okay, what does squaring something do? X squared, you might remember a parabola like this, right? If I have, I'll make a better parabola, and by better I mean kind of serving my purposes better. If I have a deviation of 1 going to a deviation of 2, right? X squared, so 1 squared is 1, but 2 squared is 4, right? So squaring values, or squaring deviations rather, shouldn't be generic. Squaring deviations amplifies large deviations. And therefore, in a way, kind of penalizes you for having those large deviations. Penalizes is the wrong word, because it's not a bad thing. It's just then you've got bigger spread, right? Hey, we already did it, so why not? Standard deviation. I know I still have time, but I always forget to give breaks. So then I try to end a little early. Anyways, so like we were saying, the standard deviation is the square root, the variance. We already said it. One of the nice things is that the standard deviation is going to have the same units as the data, right? Age, years old, right? So then the standard deviation would be the spread in years of age, whereas the variance would be age squared, and that gets tricky again, right? So there's lots of reasons we use the standard deviation instead. Okay. We'll end there for today, but I encourage you to read the rest and kind of see what's going on. And I'll post that assignment. I'll post the one for this one as well. There's a couple of things you won't be able to do, but I'll be on a roll, so I'll give you more time. If you have any questions, let me know. Otherwise, have a great weekend.